All right, so let me just, we can begin. The first talk of this session is by G Arun from CMI, Chennai. And the title of the talk is Tests of General Relativity Using Compact Binaries. So I think you can begin, Arun.
Yeah, sure. Thank you, Sumati, and thank you, Sriram and other organizers for the invitation to this meeting. And I also wish the newly instituted center all the very best in its all its future endeavors. Okay, so I'll be talking about carrying out tests of GR using compact binaries. This is a very general terminology, but I will mostly be focusing on gravitational wave observations and how they could be used to test a GR. I will explain some of the subtleties and some of the pros and cons and so on. So just to begin, this is the catalog that we have now got of gravitational waves across 3 observing runs, O1, O2, and O3, A and B. This, I think that this contains a lot of details. Very broadly speaking, it contains around 90 sources with astrophysical probability higher than 0.5, of which 85 could be called binary black holes, and the 3 could be called neutron star black holes, and the 2 could be called binary neutron stars. So these are compact objects constituting of neutron stars and or black holes. So when I said approximate numbers, maybe Anuradha's talk will tell you the subtleties in calling what is a binary black hole versus what is a neutron star black hole. I will not go into any of these things. This is just to showcase where we are in terms of the observations, and I will not talk more about it. Okay, so now let me give you a very simple motivation why we want to carry out this test of GR. Firstly, there is no reason why GR should be the correct theory of gravity. And secondly, we can test it in several ways using several kind of observations. Right? So this is a very simple enough motivation, at least for me, to carry out tests of GR and ask the question whether is there any evidence for any beyond GR physics in the data and the observations. So just to summarize, a few of the tests of GR could be put in a 2-dimensional plane characterized by phi, which is like a gravitational potential in some sense, and r is some curvature scale. And on the lower bottom thing, you can see solar system type experiments. And as you go to the middle, you will see binary pulsar test. And as you go to the right top corner, you can see gravitational waves. And gravitational wave signals, they're like straight lines, which means they are evolving as a function. I mean, as we are observing, they are rapidly evolving stages of the compact binary mergers. So basically, gravitational waves gives us a way of carrying out this test of GR in a highly nonlinear or highly strong field regime, which is dynamical because it's the wave emission is happening and a very strongly dynamical regime associated with the compact binary mergers. Now let's ask about what do we generically expect out of a modification to GR. There are many ways of approaching it. I have just taken some figure from a review article by Bertie and others, where they invoke Lovelock theorem to talk about how we can break GR and get the modified theories of gravity by invoking, for example, extra fields or higher dimensions or weak equivalence principle violations or diffeomorphism invariance violations and so on. There are different ways according to this way in which you can break or modify GR. They in turn will give you various types of sub-theories. It could give you non-dynamical fields and dynamical fields and massive gravity, etc., etc. But this tells you kind of from a theoretical side, in some sense, at least one way of approaching it to see this how all we can break GR or modify GR to get a new theory of gravity. Of course, a very hard problem, as anybody who has worked on it would see, that it's very, to formulate something self-consistent and so on, it's hard, but this is what we can expect generically out of this. Now, so our question will be to ask that how would gravitational waves in modified GR theories would differ from that of that in GR. So there are, very broadly speaking, in terms of gravitational waves, it can differ in the way they are generated. It can differ the way they propagate, or it could have additional polarization content, could be different from the gravitational waves in GR. This is just a category as far as gravitational waves are concerned about how these modifications can happen. Now, more detail. So when I say generation of gravitational waves, I mean, the generation of gravitational waves could be affected by the presence of additional fields or correction to curvature or the presence of higher dimension. And when I say propagation, it could be dispersive propagation as opposed to non-dispersive propagation in GR. There could be birefringence and so on and so forth. And when it comes to polarization, we know that GR has got only two types of polarization, the plus and cross, whereas a general metric theory of gravity can admit up to 6. And there can be presence of non-GR modes of polarization, whose evidence should also be there in the gravitational wave observation. So all these features can in principle be put to test using gravitational waves, though the bounds you can expect will vary. That will depend upon the sensitivity and the kind of method you invoke, and so on, a bit of details. So this is just to give you a general framework as to what we can expect in terms of gravitational waves from a modified theory of gravity. So this is the standard slide, which I will come back to again and again. So this is the typical dynamical phases of a compact binary. So these are two compact objects, by which I mean neutron stars or black hole, which are falling towards each other. And they have an initial stage where they are slowly in spiral due to gravitational waves, because there is emission of gravitational waves, which leads to loss of energy, angular momentum, and so on, which brings them closer. The initial stage, when there can be approximated dynamically with can be represented by a slow motion weak field type of approximation, the post-Newtonian approximation. Then they come closer, then of course this approximation will break down because things are evolving quite rapidly and you cannot anymore apply the slow motion weak field approximation. So then you need to solve the dynamics using numerical relativity simulations. You really solve the Einstein's equation on a computer. And that leads to, so that happens when they are very close to each other, they're almost when they merge. And once they merge, there's a remnant that is formed, and the remnant can have a lot of can be deformed and asymmetries and so on. This asymmetry, so the deformation, which will radiate away in the form of ring down. And the late ring down again, that is towards the end of this, this could again be well approximated by a black hole perturbation theory. And that is again analytical. So it is in between. The early in spiral is analytically can be tracked, and the late ring down is also analytically tracked. In between this phase where when these two black holes really become one, that the late stages of its evolution is something where you need to where a lot of dynamical things happen, and you need to invoke numerical relativity to solve this kind of the dynamical evolution at that stage. So this is important to appreciate about the early in spiral late ring down, because some of the tests which I will talk about will make use of this. Okay, now let's ask about how can we test in general. So I mean, ideal thing to test is that if you have specific waveforms, so the predictions from these modified theories of gravity, then it's very simple. It's simple in terms of formulation. There will be additional free parameters which represent this additional physical effects in the modified theories. You could use data to constrain them and ask whether how well can we constrain them, or is there a deviation. Or in more generally, you can do a model selection between GR and this competing model and ask, what does data support? Does data support GR more than modified theory, and so on. So that is all possible if you have a reliable, accurate waveforms from modified theories of gravity. But unfortunately, that doesn't seem to be the case, at least as far as gravitational waves go. There is a lack of accurate waveforms in modified theories of gravity, which actually stretch across in spiral, merger, and ring down, because most of our, as you have seen, our sensitivity is most to the phase before the merger. That's when the strong emission of gravitational waves happen. And we still do not have a very accurate waveforms for many modified theories of gravity, which model this late in spiral merger part of this. To make it worse, many of these alternatives to gravity, alternatives to GR, don't even have a well-posed initial value problem, and so that becomes another problem to deal with before you even start talking about numerical relativity simulations and so on. And however, there are progresses more recently on the analytical as well as on the numerical front in the case of scalar tensor gravity. And they have been encouraging. And at least more recently, at least this week, the IAP group have got a gravitational waveform, a phasing formula up to 1.5 pn in scalar tensor gravity. And there are equally efforts going on to get solve the scalar tensor gravity, obtain scalar tensor gravity waveforms in the context of numerical relativity. Of course, these are hard problems. You need extensions of GR apparatus to include many fields and so on. But however, there are ongoing efforts which are encouraging. But right now, this is not something which we can hope to employ directly in search of any non-GR physics. So what we do is to make the best use of our GR understanding, because we have a very accurate waveforms from GR for this thing, making the best use of analytical and the numerical relativity. And why don't we make use of that? So basically, our policy or our philosophy is that the theoretical limitations in understanding alternatives to GR shouldn't stop us from carrying out tests of GR. So we make use of the best understanding of the GR dynamics and the corresponding waveform, and ask whether there are deviations from this GR waveform. Now, this is a very general statement, as you can see. And so these tests are called null tests because we are talking about deviations about GR and introducing new parameters. And we ask whether these additional parameters in whatever context or these differences are consistent with GR or not. And these are called null tests. And null tests can further be subclassified as consistency test or parametrized test. So in the first class of tests, you look for overall consistency of the data with the GR prediction, whereas in the second one, you invoke specific physically motivated parameterization of the GR waveform or deviations of GR waveform, which will represent certain types of non-GR theories, and ask for bounds on these parameters. So I will be talking about these two methods in this coming thing in more detail. So in this talk, I will talk about 3 types of tests of GR, and only that because I don't want it to be an overview. I wanted to focus on this test, their basic philosophy, and what do they search for, or what do they look for, and what is the latest bound from them. And also, what are the pros and cons? What are the advantages? What are the criticisms of this method? Because all of them come with its own assumptions, and it could be questioned in various contexts and so on. It's good to understand them critically so that we know where these different tests stand. Okay, so the first test that I'll talk about is called the residuals test. It is a consistency test. So what we do here is that there is data. From the data, we subtract off the best fit. Read it as maximum likelihood waveform from the data. So you have made a detection, you carry out a GR parameter estimation, you got a maximum likelihood estimate of the parameter, and there is a waveform which corresponds to that. So you subtract off that waveform from the data, and if everything is fine and so on, you would expect that the residual after subtracting off will be consistent with noise. So in other words, there is no coherent remnant power in the residuals across detectors. If there is something coherent, then it's something we need to worry about. So if the residual is consistent with the detector noise, of course, that shows statistically it is consistent with GR. And how do we assign? How do we assess the consistency with GR? We can use it to the p-value. So p-values will assess what kind of how consistent it is with GR in the context of a null test, like we always do. Right. So what is shown here is a picture which is a bit more complicated. So let me explain. So this is on the x-axis is called the signal to noise ratio of the GR template, and the y-axis shows you the residual SNR, the SNR that I mentioned in the previous thing. It's a 90% upper limit on the residual SNR, and this shows. So after carrying out this test on the entire population of sources, this shows you where they stand with regard to the population, and the p-values are shown in this going from this maroon or whatever this color is, violet to the green. And so this is a test on the entire population, and you can see there is no specific trend. So if you expect the null hypothesis to be true, that is things are consistent with noise, you would expect the p-values to be uniformly distributed between 0 and 1, and that is what we see. There is no particular structure in this two-dimensional plane which spans the SNR and the GR versus SNR upper limit on the SNR from the residual in this plane. And this is, at least this is, shows you all the events that we analyzed so far. This diamond, and there are different types of things. They are just to distinguish from the from the first observing run, second observing run, and so on. Don't worry about them. So the basic thing is that this seems to be, there is no particular structure in this thing, which means, at least intuitively means, that the p-value is between 0 and 1. And the more rigorous way of showing the same thing would be to, on the entire population, we can get a p-value versus cumulative fraction of events plot. That is what is shown here. And if the p-value is uniform between 0 and 1 for the entire population of events, you would expect the p-value to be this thing to lie, the null hypothesis to belong to this diagonal thing. And this green one, sorry, the blue one shows you the GWTC3, which is the third catalog. That means all the sources we analyzed so far lies, and there is, it's well, there are some ups and downs, but they are all within the error bar, which constitute this shaded region. It's all within the error bar. So statistically, within the statistical error bars, there is no evidence for any deviation from GR using this method on the GWTC3 events that we analyzed. Now, it's good to understand what are the advantages of this method and what are the limitations. So, of course, the advantage is that it's a very intuitive test. It seems to be the most general test we can do. We just subtract out the GR waveform from the data, and we look for whether the residual is consistent with GR, and it's clean and more general. And it doesn't invoke any additional parameters and so on, which you have to worry about what they mean and so on. So in that sense, also it's kind of advantageous. But the limitation is that, of course, it may be the most general test you can do, but it's probably not the most sensitive test you can perform, because when you subtract off, there is no guarantee that when you compare the efficiency of various tests, it's not the most sensitive test in terms of detecting a possible deviation. And the other thing is that, of course, the first thing that will show up as a deviation is probably the systematics. There may be effects which are not accounted for in the waveform, which is the waveform systematics, and it is much more sensitive to the waveform systematics than other tests we do, for obvious reason, because we are just subtracting out two waveforms, and what will remain most likely is the waveform systematics. But anyway, so while this is a very interesting test and a very general test to do, it may not be the best candidate to first detect any possible deviation. But again, it's a very interesting, complements many other things and so on. So that kind of brings me to the end of the first test that I'm going to do. This is the residual test, where we have just, it's very general test where we have subtracted off the best fit GR waveform from the data and asked whether the residual is consistent with GR or not. Okay, let me go to the next test, which is called the parametrized test of inspiral. So this test, as the name indicates, it parameterizes the inspiral phase of the binary evolution, and in the hope that these various parameters we invoke will have some meaning, and we constrain them using the data. So we are invoking a specific parameterization. So what do they generally do? So we introduce parameters which are physically motivated. So these are free parameters to which we can attribute a physical meaning, and of course these free parameters also capture how different is the physical effect of this parameter different from GR versus some other theory. So you would expect that in a different theory of gravity, it could be different. And as a result, when you get these bounds, you should be able to map onto some specific alternative theories of gravity for which you know the predictions of it to be different, and so on. And it's a very, this framework is very widely used both in the solar system experiment as well as in the binary pulsar test, been largely successful. This PPN and the PPK correspond to the parameterized post-Newtonian thing in the solar system, which characterizes the different components of the metric of the solar system. And the parameterized post-Keplerian one refers to the various Keplerian or the post-Keplerian evolution of the binary orbital elements of the binary. So this has been largely successful. So I'll be focusing on the inspiral test, whereas Shilpa's talk in the afternoon should talk more about the ring down. So we can also parameterize the ring down, but I won't have time to go into the ring down type test here. Okay, so let's go into more detail. So I mentioned that the inspiral part is that can be well modeled accurately using post-Newtonian approximation. And if you look into the frequency domain gravitational waveform using post-Newtonian approximation, so frequency domain is more important because gravitational waves rely on match filtering, and match filtering is much better done in the frequency domain. So there's an amplitude and a phase you can see, and the phase is, we are more sensitive to the phase evolution. And the phase could be decomposed in terms of there's a TC and phi c, which correspond to the the time of arrival and the phase of arrival of the signal. And then there is this expansion. So you can see there are this expansion which contains powers of v as well as powers of v log v, right, as can be seen. So this is an expansion, and we know it up to the v by c raised to 7 for compact binaries in full generality. And the phi k and the phi kl, which characterizes the non-log and the logarithmic term in this expansion, would contain the masses, spins, and so on, all the parameters which describe the binary. It may be tidal things also, depending upon which it comes. So the binary parameters are inside this phi k parameter. So that is an important thing to carry out. And eta is just a way to define the mass ratio. There's no eta here, so I don't have to talk about it. So basically, the post-Newtonian coefficients are functions of source parameters, and they carry various physical effects, because when the wave propagation happens, there are many interesting nonlinear interactions that happen as the wave propagates, and they're all captured by these various post-Newtonian terms. So let's quickly examine what they are. So we can forget about the first two, that there's nothing to it. So 1.5 pn, you've got the tail effect, which is tail effect is when what happens when the interaction of the wave that is propagating gets scattered by the background space-time. And also at the same order, 1.5 pn, that is v by c cube, you have spin orbit interaction. If the binary spin is non-zero, it could be interacting with the orbital angular momentum. At 2 pn, you start seeing spin-spin interaction. And at 2.5 pn, of course, so these are the first pn order at which this effect appears. And as you go higher, and you can look to 3 pn has got tails of tails, which are again tails being scattered again by the background curvature, and so on, and tail square. So there are various types of interactions which happen as you iterate Einstein's equation to get the post-Newtonian flux and the phasing and so on. And all these effects happen at different pn orders. And the good thing and the bad thing about this is that at different positive, so at every order above 1 pn contains more than one physical effect, because as you iterate more and more at different orders, there can be more than one physical effect, which of course is good in the sense we are sensitive to a mixture of physical effect. At the same time, it is a problem also, because if you see a deviation in the future, you do not know what you would attribute that to. That is a problem, but that probably is a problem you would look into after you see something. So the point I want to highlight from this is that the post-Newtonian phi k and the phi kl, which I mentioned, capture a lot of physics in terms of the binary evolution and the various interactions it undergoes. And hence it is very rich. And you would expect that these interactions are in GR and in a modified theory of gravity need not be the same. It could be different. And these differences would be captured by invoking, parametrizing this phasing formula like this. So what we do on the right-hand side, we can look at these equations. So we make this phi a, which was there, the phi k, phi a go to phi a gr plus some delta phi a. This is the deformation that we are introducing. To make it simple, we just scale out phi gr so that we can make this dimensionless, and we call it delta phi hat a. And as is clear that delta phi hat a gr is identically equal to 0, that is the parametrization. It's a null parametrization. So what we will do is to use this parametrized waveform in the analysis, obtain the posterior distribution on this delta phi hat parameters, which could look something like this, right? And you would expect ideally if the GR is 2, it should be peaking at 0 with a width which is due to the noise that various sources of noise that is present, and the width of this will give you some bound on the value that it can take. So this is how it is kind of formulated, and this is what we invoke. And this, so basic thing to keep in mind is that this additional parameter which I introduced captures the different physical effects which are there in the compact binary dynamics. Okay, so let's see what does it test. As I said, it tests for how consistent the physical effects are in GR versus a modified theory of gravity, and or in other words, are in general the phasing coefficients. Is there a consistency of the phasing coefficients with the predictions of GR, or is there any hint of deviation? Okay, with that, I think this is the plot that we have got. So what is shown here is so we carried out search for O1, O2, and O3, and we found no evidence for any possible deviation, which allows us to put limits, upper limits on these deviation parameters. And these are exactly the bounds on 5.0 all the way up to 5.7 is what is shown here. And you don't have to pay attention to this color coding. It shows you the individual events. So because this is a combined bound, combining the information from all the events, and that is what is shown here. And the joint bound from GWTC3 is this this blue one. And you can see that the bound on that, this is the d phi naught hat, for example, delta phi naught hat. It is, it's more than 10 raised to minus 1, or it's a few times 10 raised to minus 2. And you can see for almost all of them except one, the bound is better than 1, which of course, at least it's 100% in some sense. But for many of them, it is close to, it's comparable to 10 raised to minus 1. So you can see that all the Pn coefficients up to even up to high orders are bounded to some accuracy depending upon sensitivity after adding these parameters. So there is, it's all constant with GR with a width that is less than 1 for most of them. Now, what is shown on the left thing in isolation is the minus 1 PN1. So this shows you that in the GR there is no dipolar gravitational waves, and if there is a dipolar emission in some theories of gravity, such as scalar tensor theory, it could give you a minus 1 PN term. So with regard to this phasing formula, it could give you, it can give you some this V phi. It could be V cube in some sense, 1 by V cube. So this can also be tested, and this gives us, because it's a very low frequency kind of effect, it helps the more number of gravitational wave cycles you have got, it improves the bound, and the bound from combining the binary black holes and the neutron star black hole is the best one. So it's typically of the order of 10 raised to minus 4 at few times 10 raised to minus 4. This that is a more stringent bound, we can say. So that is the bottom line. This gives you the state of the art in terms of constraining the post-Newtonian parameters from the GWTC3. Now, this, as I mentioned, this contains analysis of BBH and the NSBH signals. There are a few interesting cases in this GWTC3 catalog. So the one interesting case is something which happened during the second observing run. It's a binary neutron star merger, 1708-17, which actually gave us an opportunity to test GR in presence of matter effect. So when two neutron stars are merging, there's tidal interaction, there is a lot of neutron-rich matter around it. We can ask the question whether the GR is still valid in presence of this matter, because there can be effects, fields, whatever, which can be which may turn on in presence of matter, which we cannot do otherwise, because the BBS tests are mostly vacuum. They are vacuum spacetimes, and we get this bound. So we can see that this is a binary neutron star with a total mass of around 3 solar mass to 0.8 solar mass. It's a very long in spiral. It merges at the almost outside our sensitivity band, and so on. But we get extremely good bound on the minus 1 PN1, so it is comparable to 10 raised to minus 5, or the order of 10 raised to minus 5. And of course, as you go to the higher PN1, the bounds are much worse compared to. We can see that here it's 10 raised to 1, whereas if you go to here, it's like 10. But if you compare with 0 PN, which is you can see that the bound from the binary neutron star alone is comparable to what we have got by combining all the binary black holes and the neutron star black hole and so on. So mostly the low frequency evolution is what happens in the heart of the band. We are more sensitive to it. It gives us very good constraints on the lower post-Newtonian coefficients, whereas the higher post-Newtonian ones, the evolution is mostly outside or in the least sensitive part of our noise floor, and hence it gives us weaker constraints on the higher PN1. But it is still interesting because this test is unique, because it tests for GR in presence of tidal interaction, because that's something which couldn't be done with other kind of systems. There are two more interesting cases in the catalog. Both happened during the O3A, the previous observing run. These are two events, 1908-14 and 1904-12. In the case of 1908-14, it shows you strong evidence for higher modes. So these are non-quadrupolar mode. You can, in the spherical harmonic sense, it is 3-3 mode, which is very strong evidence. It shows you the signal to noise ratio can be comparable to 6 and so on. Whereas there is no precision. So this is what is expected from the noise, and precision is constant with noise. So there is no precision here. It happened to be almost non-spinning. But there is a strong evidence for higher modes here. In the case of 1904-12, it showed weak precision because it is slightly offset, and some evidence for higher modes. But however, these two are important because these are the two events for which we showed very strong evidence for the presence of higher modes. And earlier, all the tests we were doing, or all other tests we have been doing, is only on the quadrupolar thing. So we have been talking about the phasing evolution of the quadrupolar wave, whereas these two bounds, which are part of, so I show you all these things together, but some of the bounds, two of the bounds which has gone into this is actually coming from these two sources. And I want to stress that this is a very important thing. These are the only two sources for which we have tested the validity of GR in the non-quadrupolar approximation. So octopole in this case here, right? So this is again an interesting thing. So the interesting thing to keep in mind is that we want to test GR in various regimes, in presence of tides, in presence of higher modes, in presence of strong precision, and so on, because we do not know where this deviation will show up. But they all will be, at least in this framework, they all will be part of this test. The bounds, which will, the constancy of this bound will capture all these effects in one go. Okay, so that is that is the bounds that is there from this parametrized post-Newtonian way. But let's now look into critically about what could be the possible criticisms. There have been many criticisms about this method from the time we proposed, and most of them come from not thinking deeply about it. So the first objection is that people think that one can test GR only if there is a modified theory of gravity, and but that is not the point. So we are introducing null parameterization about GR, and we look for deviations about that, which could be mapped, which may not be mappable, depending upon the availability of the same post-Newtonian term in an alternative theory of gravity. So that is the confusion, that without having a theoretical backing, what would these bounds mean? And these bounds simply mean how well we can test the physical effects in GR. That's the simple answer to that. But there's a more important technical point to this that I did not stress either. So when I quoted these results, they were on top of the GR parameters. These bounds are obtained varying only one parameter at a time. So there is this post-Newtonian structure, and there are 8 of them I mentioned. So these are obtained by assuming, keeping all the GR parameters intact and varying only one at a time. So this is one at a time is what is obtained. And it is quite reasonable to ask that what does it mean to carry out the single parameter test? So we keep only one deformation at a time, when we expect that a modified theory of gravity could be modifying more than one for sure, right? So it is a valid objection, but it is a limitation that we cannot carry out this test. But once you try to estimate more than one at the same time, it gives you an informative thing, because there is so much information in the data. You cannot carry out multi-parameter tests with the sensitivity we have currently got. And this is due to the degeneracies we have got with masses, spins, and so on, and with this non-GR extra parameter that we have introduced. And it has been shown that one way in future we can overcome that is to carry out multi-banding, which is observing the same source in 2 bands. Once space-based detectors are operational, you could combine space-based detectors and ground-based detectors and try to complement each other. That could give you this multi-parameter test thing. But it's not an objection, because still as a null test, if there is any deviation in any of the one, we will still be capturing that. Of course, it is true that once you see a deviation, it may not have a unique interpretation as to what exactly is going wrong. But that again is a post-processing, it's a post-detection problem. And at that point, we should be concerned about this objection. But with the sensitivity, this is the best we can do. And as a null test, there is perfectly fine. There is no issue with that. But in between, we can ask the question that, since we cannot measure all of them at the same time, is it possible, even for advanced light type detectors, to identify, if we cannot constrain all of them, is there a linear combination of them which is best measured? In that sense, the linear combination is sensitive to all the parameters, because it's a combination of all the PN coefficients. And this is a test that was done recently by Anthony, who is my PhD student. And what we found as a first cut estimate is that so what is shown here is the PCA1 is the first linear combination. This is the red one. And the second PCA is mostly uninformative, which means that with the sensitivity we have got, almost all the thing gets dumped onto the first leading linear combination of the 8PN1, and that is what is shown here. Is constant with GR combining. This is after combining only the first events of the first two observing runs. So this, of course, is a very promising way to go ahead. Of course, we need to understand more, and we are in the process of analyzing the data for the O3 and the events from O3.
Arun, we have 5 minutes left.
Okay, perfect. Yeah, fine. I think I'm there. Okay, so now with that, let me go to the next one. Is the last test I want to discuss about the inspiral merger ring-down consistency test. So this is actually looks for consistency between the mass and the spin of the remnant black hole, inferred independently from the inspiral part and the post-inspiral part. So what do I mean? So I break this this signal into two parts with this dotted line, which is on the left is the inspiral, on the right is the post-inspiral. I use numerical relativity motivated fitting formula, which maps the initial to black hole final mass M1 chi1 to final black hole mass and spin. I get two estimates of the final mass and spin, that is the remnant black hole mass and spin, the blue and the red one, and ask the question that are they are they equivalent, are they in agreement with each other? So this, in some sense, is an agreement between the low frequency part of the waveform and the high frequency part of the waveform. Are they consistent with each other? It's like a self consistency of the waveform itself. Right. So what it is sensitive to is actually there are anomalous loss of energy and angular momentum which cannot be explained in the process of the merger. It can directly detect that because there is something lost between the inspiral and the ring down. It's a very powerful test of the merger dynamics. In my opinion, the only one which we can currently, why we trust the merger should be intact with GR is because this test give you very good evidence for that. Okay, so as this is mentioned, we construct this null variable. The delta MF is the difference between the final mass estimate from the inspiral and the post-inspiral, and we get the posterior distributions on the final mass and the final spin. We make it dimensionless by dividing it by the mean of it. So you can see that this is a result from the latest catalog. They are all consistent with 0. You can see the red is the spin and the blue is the mass, and you can see they are consistent with 0. There is nothing showing up in this here as well. So just about the pros and cons, it's a very useful probe of the merger dynamics. It's a very smart combination of the parametric method with the consistency test. It's a combination of both in a very healthy balance. And the con is that it's a limited applicability because to carry out this test, you need good signal to noise ratio in both the regimes. So it's a bit of a limitation. And right now we are using NR fits to obtain the final mass and spin, but eventually we may be using ring down estimation independently in the future, but currently we don't have sensitivity to do that. So that's another kind of limitation or the drawback of this method. Okay, so the status, this is the latest paper from the LIGO Virgo Kagera collaboration, which did 9 tests on this, on various tests of GR, and we found no evidence for any beyond GR physics, and everything is consistent with GR lies well within the error bars of statistical error bars. So what does it mean? Either it means that we are, our sensitivity is not good enough to detect a deviation from GR if present, or it may be that the GR may be violated in an extreme region of the parameter space, like high precision, high eccentricity kind of thing, which we don't know. It could be both, right? So we should keep on testing it by improving these methods, and that's the way forward. So looking forward, I think if you want to claim a violation from GR in the future, if there is anything, you need to control the waveform systematics very well, such as effects such as eccentricity. There's a talk by Pankaj Saini tomorrow on this. And also, we need to have a very good understanding of the detector noise. And there can be non-stationarities and non-Gaussianities which can mimic violations from GR. We need to have complete control over these effects. And in terms of improving the null test, we need to improve our waveform accuracy and accounting for all the physical effects. And also keep a close watch on kind of adapt the most recent developments in the modified GR theoretical modeling, because you should use them to the best of the ability to carry out such tests. And also assess the sensitivity these different tests will have on taking possible deviations. And there are some effort by Nathan Johnson McDaniel who compared the efficiency of various types of tests on a mock GR violated signal. Okay, I conclude. So what I've shown you is that the tests that we have carried out so far shows no evidence or support for any beyond GR physics. This suite of tests is they're admittedly not independent of each other, but complement each other in a very nice way by methodology and algorithms and so on at every level. And the improved tests in the future should capture the essence of the most recent analytical or numerical developments from the modified GR computations. And the future improvements in the waveform modeling and the detector noise characterization. I would like to stress that it's not just the waveform modeling, the detector, understanding the detector noise is also equally important in the future if you want to carry out this test very efficiently. With that, I'll stop and take any questions. Thank you so much.
Thanks, Arun. Thanks for a really excellent talk. And thanks also for finishing exactly on time. So I want to keep the floor open for questions. Please raise your hands or write your question in the chat box.
You can unmute and speak and ask the question.
Right. Okay.
Hello.
Yeah,
Hey, Arun. So I just wanted to ask a couple of things. Maybe it will motivate others to speak up also. So in the very first slide, one of the first slides you mentioned this birefringence.
Yeah.
So this is the effect that different polarizations behave differently. Is
correct. Yeah.
Okay. And in also one of the first tests you discussed, there was a slide where you had green points and purple points. This slide. What is very curious is that all the green points are in the lower half and the purple points in the upper half. Is there any physics associated to that, or this is some?
No, I think this should be fine because the one thing to keep in mind is that the violation of GR plus N it's not directly proportional to the SNR because you translate this onto the what is called the fitting factor, which characterizes a mismatch between the GR and the non-GR waveform and so on. So as long as this plot, which captures all these features within the error bar, this is consistent with the diagonal thing, which is actually a continuation of this plot. This is, as you can see, the diagonal is a null hypothesis, and this is showing, and this gray region shows error bar with due to various things. As long as this is lying without this should be okay. Is what I would think. And because it can also be, as I said, there can be waveform systematics. And maybe it is true that maybe certain class of sources consistently demand some physics which is not accounted for, and these small things could show. So that could be responsible for this. But other than that, as long as this is a more conclusive plot, is showing consistency, it should be fine. There is no need to think there is any violation also.
Thanks.
Someone else is asking a question. Yeah. First Raghu. Hi.
Hi. Arun, in all of these tests and studies, does anyone consider the possibility that these could be due to mergers involving naked singularities?
I think there are some works along those lines. So I think what I did not talk about is that I talked about a test of GR. There have been a pool of work about them being exotic compact objects of some type. It could be boson stars or gravis stars or even naked singularities and so on. I think there are some theoretical problems. I think, for example, we need a waveform with naked singularities to look into this. I think there are issues in terms of. So I think one thing, one test which can be done is about the remnant black hole. Whether the remnant black hole as a naked singularity is probably easier thing to do. And for example, people look for whether a spin, the naked singularities may not have the spin limit of 1, right? I think such things have been done to some extent, but I think even then reliable or I shouldn't call reliable, but accurate model about the predictions of naked singularities probably has not been explored. But I'm also not an expert, but I think I have seen some papers which talk about the remnant black hole property and its consistency with the naked singularity.
Next question is Sriram.
Arun, I have a naive and simple question. Does this account for changes in the trajectory in a modified theory in addition to the changes in the waveform?
Yeah, I think because here once you I think once you are a nonlinear regime, there is no difference. So you're looking at the overall dynamics. So the all that we are mapping everything onto the facing. So the facing will contain all these things. So if any prediction of the non-GR theory that is concerning the dynamics of the binary will be encoded in the facing coefficients, which will involve both these things, and hence it is sensitive to all kind of changes you can expect onto the post-Newtonian coefficients.
Is one more dominant than the other, the dynamics versus the emission mechanism?
No, so I think, see, in the perturbative regime, that is post-Newtonian one, you expect adiabatic approximation, where you assume that the time scale for shrinking is small compared to the orbital time scale and so on. But once you get into the dynamical regime close to merger, this is no longer true because very rapidly going and this time scale become comparable. So you cannot, basically the breakdown of the adiabatic approximation would make sure that there is no time scales are comparable. Hence, they cannot be separated in some sense. So they would both contribute towards the late stages.
There's one last question. Sorry, Sriram.
Go. I'm done. Thank you, Arun.
There's one last question. Well, there's two now, but I'll first go with the one that's in the chat from Piyush Marma, which is, what is the difference between PPN and PPK?
Yeah, so I think the difference of PPN. So PPN is something which is employed for solar system test, where we have got a sun as a static spacetime of sun. You look into the metric components of sun or the central object, and you introduce deformation on every non-zero component, every component of sun, right? And whereas in the case, so that is adapted to the solar system test. In the case of post-Keplerian parametrization, you're looking into binary pulsar orbiting around each other. So what you're looking for is how the orbital elements evolve due to the radiation reaction or due to emission of gravitational waves. So the post-Keplerian parameters would be looking into how the periastron precision would be changing due to the emission of gravitational waves and so on. So that parameterization is on the evolution of Keplerian or the post-Keplerian parameters, whereas the PPN would talk about the change in the metric components of a weak field system like sun in this case. So that's the difference between the two.
So we're running a little late, but if the question by Lakshman is short, please ask your question now.
Yeah, it is short. So, so you mentioned in the parameterized test, like we have this phi cap, which was the general parameter. So why do we need the multi-parameter test? Because phi could be anything. I don't understand that.
Yeah, so I'm saying that suppose you consider a modified theory of gravity, it is not incorrect to expect that. Suppose your first correction to the GR facing formula is at 2pn, correct? Then it is not incorrect to assume that starting from 2pn, it might be changing all the pn coefficients from there on, right? 2pn, 2.5pn, and so on. It can be that's not unexpected. So in that case, the question is that, when you do one parameter test, how would this capture multi-parameter deviations, which may be predicted by a subclass of non-GR theories? And that is the question. The answer to that question, as I told you, is that we are doing a null test, and even if once you change it, we'll be detecting a deviation. But a unique mapping between this modified theory and this bound will not be possible without having this multi-parameter bound.
Okay, thank you.
Thanks, Arun. Thanks for all the people asking questions. I'll ask you my questions later.
Yeah, sure.
So thanks a lot, and let's give a hand
Thank you so
to
much.
Arun again.